Not so distant time ago, I was working on a requirement for work when I came across this. Younger me would look at this code and say, hey, this is pretty good. I mean, composition's always better than inheritance. Today I look at this code and I think to myself, this has 16 dependencies. 16! Then I'd probably just move on and not worry about it. But then, I realize I've seen something like this before. And again. And again. And again. This is not best practices. This is a trend, and a bad one at that. For this example, we're talking about dependencies that are interfaces. But the problem would still exist if you're using dependencies that are concrete types or abstract types. Actually, let's go over what an interface, a concrete type, and an abstract type are. An interface is probably the easiest to understand. In the real world, the interface is congruent with what an interface is in the software world. In the real world, I have a device that has a power button. And when I hit the power button, the device turns on. In the virtual world, video game for example, I turn a virtual phone on by interacting with the virtual phone's power button. In the real world, I interact with the phone by physically hitting the power button on the phone to turn it on. In the virtual world, I'm not actually physically hitting anything. I'm sending a message to the virtual phone's power button functionality. In both scenarios, me being the physical user, or a digital avatar in the virtual world, do not care how does the phone turn on. We both just care that the phone does turn on. The implementation of how the phone does turn on is a black box to the entity that triggered the interaction to turn the phone on. Therefore, an interface is just the means for an entity to define its interactions externally to the world. This is a concrete type. A Google Pixel 6 to be exact. Implicitly, this has an interface by default. I can interface with this concrete type by hitting the power button to turn it on, and I can interface with this concrete type by turning the volume up or turning the volume down. Similarly, a concrete type in the software development world has an implicit interface by default. We call this concept a class in the object-oriented software development world. In the real world, knowing and seeing the Google Pixel 6 does not allow me to know how the external interface functionality is implemented. I can, however, look up technical documents for this make and model of phone to see how the external interface functionality may be implemented. Likewise, in the software development world, knowing the concrete type of the phone class still does not let me know how its interface is implemented. The difference is the implementation for that concrete type exists in the concrete type class specification. Therefore, a concrete type in software development is both the external interface as well as the implementation for that external interface functionality. To reiterate, this is from the user's perspective interacting with the phone, the external actor. In the real world, that is you, or it's me. In the virtual world, it is some digital avatar, or more specifically, it is just another class interacting with the phone. So to recap, an interface is the means for one entity to interact with another entity, like a user turning on a phone. An interface is a definition of all the externally available functionality that an entity can act on. The concrete type specifies an implicit external interface, as well as internally detailing how those interface interactions are implemented. This just leaves what an abstract type is. An abstract type is just a combination of both an interface and a concrete type. It's a superset of an interface in that it provides all the external functionality available to consumers. It does not need to implement every single internal implementation detail like a concrete type, though. Fundamentally, all types, an explicit interface like the example at the start, an abstract type, and a concrete type, all share an external interface that another class can call. The relationship of what the class can call for that external interface is the important factor. It should make sense. For example, does a user check the battery life of a phone before it hits the power button? Or does the user hit the power button and the phone indirectly checks that the power in the battery is enough to turn the phone on? Does a person who shows interest in purchasing a product, a prospect, directly interact with the company when showing interest in a product? Or do they indirectly interact with the company when showing interest in that product? Similarly, does a prospect interact directly with the inventory of a product? Or do they indirectly interact with the inventory of a product when purchasing that product? There are implementation details here that the actor, the prospect processor, does not need to know or have to deal with in this implementation. So to the question, does the prospect directly interact with the company when showing interest in a product, or does the prospect indirectly interact with the company when showing interest in a product? And the answer is the prospect indirectly interacts with the company when showing interest in the product. When they show interest in the product, a message will be sent to the company that the prospect is interested. Does the prospect interact directly with the inventory of the product, or do they indirectly interact with the inventory of the product when purchasing that product? The answer is they indirectly interact with the inventory of that product when they purchase it. It is up to the company to deal with inventory and supply chain issues. The prospect themselves does not care about any of these supply chain or inventory issues. When constructing a class through composition, think in terms of, does this concept this class represent make sense to interact with all the entities it includes? For example, a person class would include a phone it can turn on, and a shirt it can put on. The person does not need to notify the company that it has the phone before it turns it on. It just needs to be able to turn the phone on when it's in its possession, just like in real life. Probably the most egregious example of this is the prospect processor needing to retrieve the validation rule set as to whether the prospect itself is in a valid state. It then takes that validation rule set and passes it to the validation service to compute whether that prospect is valid. This is a clear violation of the prospect processor knowing too much implementation details. A potential solution for this is to have the prospect processor internally validate itself. Externally, this removes the concept of whether a prospect is valid or not valid, and it also removes the external concept of a prospect validator from the solution. I've been using words like implied and implicit interface in the earlier section, and maybe once or twice used the word explicit interface. Now, a concrete type has an implied interface, but a concrete type can also implement an explicit interface as well. The main reason to use an explicit interface over the default implied interface for a concrete type is actually to hide the concrete type that is actually utilized under the explicit interface. For example, there's a difference between someone saying, "Call for help on your phone, there's an emergency," as opposed to, "Call for help on your Apple iPhone 12, there's an emergency." Since I don't have an iPhone, but a Pixel, I can't carry out that second request. I can, however, carry out the first request because all phones share a common explicit interface, and they all share the common functionality to call. This is what an explicit interface grants you: the ability to carry out a task that is shared by all entities within a classification. The explicit interface that is within that classification can be treated both as the explicit interface as well as the concrete type that it is. In other words, I can call on my phone or I can call on my Google Pixel 6. Both have the same result. However, the latter is more limiting. If I have to use a phone to call, I can use any phone that has the functionality to call, which is a requirement for a phone to be a phone. If I have to make a call on only my Google Pixel 6, I can't use any other phone device. This is where there's a drastic difference between the real world and the virtual world. In the real world, people are easily adaptable and adjust to using the proper level of specificity when carrying out tasks. To contextually change between being asked to call on an iPhone, but instead use a Google Pixel 6 is instinctual. It's effortless. In the virtual world, if I specifically commit to using a Google Pixel 6 in my application, and then tomorrow I upgrade to a newer version or get the latest Apple iPhone, the effort is significant to change. I need to explicitly change my person class to utilize a Google Pixel 7 or Apple iPhone 13. Otherwise, I can't make a call. The alternative in the virtual world is to use the explicit interface that a Google Pixel 6, Google Pixel 7, Apple iPhone 12, or Apple iPhone 13 all share: a phone. Therefore, if the digital person ever changes which phone they use, the person class remains the same because it's relying on the explicit phone interface as opposed to the default concrete type interface provided by a Google Pixel 6. The downside of explicit interfacing is picking the wrong level of abstraction for the interface. A phone is a good abstraction for an interface because it went through the rigors of time, and society benefited from the use of that classification. The abstract phone classification encompasses sub-abstract types like wired phones, wireless phones, cell phones, landline phones, car phones, as well as encompassing such specific types like the Google Pixel 6 as well as the Apple iPhone 12. The first phone was patented as the sound telegraph in 1872. It then shifted to become just the telephone because I imagine the word telegraph fell out of common use. Then, with the advent of non-landline phones like car phones and cell phones, the term phone was coined to encompass sound telegraphs, car phones, and cell phones. Just a note, I don't use telephone interchangeably with phone because telephone has a connotation with just landline type of devices, and would be thought to be excluding cell phones. If the wrong level of abstraction is picked for an explicit interface, like using only landline phones, this will exclude cell phones. Therefore, if I ever needed to make a call and can only rely on landline phones, this will be very inflexible and my options are very limited. Especially in this day and age where most households probably don't have phones hooked up to any copper wiring. But I would imagine one member of the family does at least have a cell phone to utilize. Then we can always just take the extreme example where we're relying on a concrete type like only using Google Pixel 6s. Those Apple iPhone users will definitely not be happy about that. I briefly mentioned it, but it's worth restating here. Time is what defines a good abstraction. Time is what defines a good explicit interface. The abstraction or the explicit interface is retroactively found after the creation of the abstraction's first concrete type. It is almost impossible to come up with a good abstraction or explicit interface during the time of the first creation. Revisiting our good friend the Prospect processor again, this was created on the initial release of this project. Therefore, it has not stood any test of time to determine whether this is a good abstraction. Like I said, it's almost impossible to come up with a good abstraction at the time of creation. But let's assume that they did that, and did that not once, not twice, not 3 times, but 16 times. Let's then ask ourselves then, do these 16 interfaces meet the criteria of the benefit for an explicit interface? Again, the main benefit of an explicit interface is that it hides the multiple concrete types that implement said abstract interface. Let's go line by line. iCompanyService has only one concrete type that implements the iCompanyService explicit interface, CompanyService. Likewise, iProductService has only one implementation that implements that explicit interface, ProductService. Same thing for iAgeRangeService and iProductCategoryService. Actually, this is the same for all these interfaces. Actually, if you haven't noticed, Prospect Processor implements an explicit interface, iProspect Processor. And you've guessed it, there's only one implementation for that interface as well, the Prospect Processor. So since none of these interfaces have gone through the process of time to solidify a good abstraction, nor do any of these interfaces have more than one implementation, I would say that these are redundant and useless abstractions that shouldn't exist. I would just suggest to have the Prospect Processor use the actual concrete types instead of the explicit interfaces that it currently uses to make it a little bit better. As an aside, I'm sure some of you are ready to jump up out of your seats and say, but my tests implement these explicit interfaces as concrete types. These interfaces help with testing. Rest assured, I'll cover this in another video. There's a common saying in computer science. There are two hard things in computer science: cache invalidation, naming things, and off-by-one errors. Thankfully, the example we've been looking at does not have an off-by-one error. It actually has an off-by-13 error with the number of dependencies it has. But I'd like to focus now on names. Let's ignore interfaces and concrete types for the time being, and let's just focus on the names involved. Does the name processor or service have any difference? Does the name processor or service give any more clarity as to what these things actually do? No, they don't. I can give concession to this, though. Some development teams will use the terms like service to mean this, or the word processor to mean that. In other words, terms like service and processor may exist as explicit interfaces, as external documentation for the code, but doesn't exist within the code itself. A meta interface, if you will. I'm only pointing this out because sometimes in your code, you'll come across words like processor, service, helper, or worker appended to the types of the names in your code. These should be avoided at all cost. They're superfluous. You can, however, use them if, like I said, they are decided to mean something outside of the common definition that currently exists for them. Another thing about names, some of the modifications I had to do for this code required me to look at the implementation for the explicit interface. For example, the IAssert validation rules service was originally called IAssert service. What was it asserting? 1 + 1 = 2? The sky is blue? Or maybe it could be a general explicit interface to assert anything that can be asserted. It was none of these things. It was an assertion for the prospect with the validation rules set retrieved from iProspect validation rules service. I would go even further and say that my original rename was inadequate. It probably should be IAssert prospect with validation rules set service. The biggest problem with the Prospect Processor is that it has 16 dependencies. The human mind can only hold a mental model of around 4 unique concepts at once, let alone 16. I think the improper use of interfaces and incorrectly justifying the perceived benefit of using interfaces has perpetuated the problem. I've seen examples like Prospect Processor throughout my entire tenure as a professional software developer, but I have never seen a Prospect Processor using only concrete types. My rule of thumb is don't create classes with 16 dependencies, and don't create explicit interfaces unless that explicit interface has multiple concrete types that implement it. These should exclude concrete types that are utilized in your tests. But hey, this is just my strong opinion, weakly held of course. Please, leave a message in the comments below